Probando, probando, no, estrés. Está muy alto y realmente podría ponerlo. Okay, let's rate this thing. Oh, pero. A ver. Ya se me olvidó cómo componer y hacer los análisis de negocio. Vamos a aprender de nuevo. Okay, so design in construction, design challenges part 74. Design key concepts, design building blocks, heuristics, design practices, comment on popular methodologies, software architecture, working classes, characteristics of high quality routines, defensive programming, refactoring, how to program size affects construction. It says some people may argue that design isn't really a construction activity. I need more light. Design is really a construction activity, but a small project. Some people may argue that design isn't really a construction activity, but on small projects, many activities are thought of as construction, often including design. On some larger projects, a formal architecture might address only the system level issues, and much design work might intentionally be left for construction. On on other large projects, the design might be intended to detail enough for coding to be fairly mechanical, but design is rarely that complete. The programmer usually designs part of the program, officially or otherwise. On small informal projects, a lot of design is done while the programmer sits on the keyboard. Design might be just writing a class interface in pseudocode before writing the details. It might be drawing diagrams of a few class relationships before coding them. It might be asking another programmer which design pattern seems like better choice, regardless of how it's done. Small projects benefits from careful design just as larger projects do, and recognizing design as an explicit activity maximizes the benefit you will receive from it. Design is a huge topic, so only a few aspects of it are considered in this chapter. A large part of good class or routine design is determined by the system architecture. So be sure that the architecture prerequisite discussed in section 3.5 has been satisfied. Even more design work is done at the level of individual classes and routines described in chapter 6, working classes, and chapter 7, high quality routines. If you are already familiar with software design topic, you might want to just hit the highlights in the section about design challenges in section 5.1 and key heuristics in section 5.3. Okay, so 5.1 design challenge. Cross-reference. The difference between heuristic and deterministic processes is described in chapter 2, metaphors for a richer understanding of software development. This is cool. Let's go and see this too. Metaphors for a richer understanding. Metaphor of a richer understanding of software development. Wow. There's something. Metaphor for a richer understanding of software development. The importance of metaphors, page 9. How to use software metaphors, page 11. Common software metaphors, page 12. 13. Hello. Hola. Hello, I'm doing some reading of Code Complete book. I'm reading some uh, design patterns. I might read in Spanish or English, I don't know. But I'm currently reading some design concepts so I can create classes for a program that I'm building. Okay, so let's keep reading. So this is heuristics in design. Design is a heuristic process. Okay, computer science has some of the most colorful languages of any field. In what other fields can you walk into us? sterile room, careful control at 68 Fahrenheit, and find viruses, Trojan horses, worms, bugs, bombs, crashes, flames, twisted sex changers, and fatal errors. These graphics metaphors describe a specific software phenomena. Equally vivid metaphors describe broader phenomena, and you can use them to improve your understanding of the software development process. The rest of the book doesn't directly depend on the discussion of metaphors in this chapter. Skip if you want to get to the practical suggestions, really if you want to think about software development more pretty. Let's do this. I like it. This is good to talk about metaphors, right? So So the importance of metaphors. Importance of development often arise out of analogies. By comparing a topic you understand poorly to something similar you understand better. You can come up with insight that result in a better understanding of this less familiar topic. This use of metaphor is called modeling. Okay? The history of science is full of discoveries based on exploiting the power of metaphors. The chemist Goulet has had a dream in which he saw a snake grasp its tail in its mouth. When he awoke, he realized that a molecular structure based on a similar ring shape would account for the properties of benzene. Further experimentation confirmed that hypothesis. Barbour, 1966. Nice. The kinetic theory of gases was based on a billiard ball model. Gas molecules were thought to have mass and to collide elastically as a billiard ball do. Mhm. And so many useful theorems were developed from this model. The wave theory of light was developed largely by exploring similarities between light and sound. Light and sound have amplitude, brightness and loudness, frequency, color and pitch, and the other properties in common. The comparison between the wave theories of sound and light was so productive that scientists spent a great deal of effort looking for a medium that would propagate light the way air propagates sounds. They even gave it a name, ether, but they never found a medium. The analogy that had been so fruitful in some ways proved to be misleading in this case. In general, the power of models is that they are vivid and can be grasped as a conceptual wholes. They suggest properties, relationships, and additional areas of inquiry. Sometimes a model suggests areas of inquiry that are misleading, in which case the metaphor has been overextended. When the scientists looked for ether, they overextended their model. As you might expect, some metaphors are better than others. A good metaphor is simple, relates well to other relevant metaphors, and explains much of the experimental evidence and other observed phenomena. Consider the example of heavy stone swinging back and forth on a string. Before Galileo and Aristotelian, looking at the swinging stone through that a heavy object moved naturally from a higher position to a state of rest at lower one. The Aristotle, as Aristotelian, would think that what the stone was really doing was falling with difficulty. When Galileo saw the swinging stone, he saw a pendulum. He thought that what the stone was really doing was repeating the same motion again and again almost perfectly. Yeah. Mhm. The suggestive powers of two models are quite different. The Aristotelian, who saw the swinging stone as an object failing, would observe the stone's weight, the height to which it had been raised, and the time it took to come to rest. For Galileo's pendulum model, the prominent factors were different. Galileo observed the stone's weight, the radius, and the pendulum swing, the angular displacements, and the time per swing. Galileo discovered laws the Aristotelian could not discover because their model led them to look at different phenomena and ask different questions. Hell yeah, bro. Yeah, that's right. Metaphors contribute to a greater understanding of software development issues in the same way that they contribute to a greater understanding of scientific questions. In his 1973 Turing Award lecture, Charles Bachman described the change from the prevailing Earth-centered view of the universe to a sun-centered view. Ptolemy's Earth-centered model had lasted without serious challenges for 1400 years. Then in 1543, Copernicus introduced a heliocentric theory, the idea that the sun rather than the earth was the center of the universe. This change in mental models led ultimately to the discovery of new planets, the reclassification of the moon as a satellite rather than as a planet, and a different understanding of humankind's place in the universe. Right on. Mhm. It says here the value of metaphors should not be underestimated. Metaphors have the virtue of an expected behavior that is understood by all unnecessary communication and misunderstandings are reduced. Learning and education are quicker. In effect, metaphors are a way of internalizing and abstracting concepts, uh, allowing one's thinking to be on higher plane and low-level mistakes to be avoided. Fernando J. Corbato. Bachmann compared the Ptolemaic, Ptolemaic to Copernican change in astronomy to the change in computer programming. In the early 1970s, when Bachmann made the comparison in 1973, data processing was changing from a computer-centered view of information systems to a database-centered view. Mhm. Bachman pointed out that the ancient of data processing wanted to view all data as a sequential stream of cars flowing through a computer, the computer-centered view. The change was to focus on a pool of data on which the computer happened to act as a database-oriented view. Today, it's difficult to imagine anyone thinking that the sun moves around the earth. Similarly, it's difficult to imagine a programmer thinking that all data could be viewed as a sequential stream of cars. In both cases, once the old theory has been discarded, it seems incredible that anyone ever believed it at all. More fantastically, people who believed the old theory thought the new theory was just as ridiculous then as you think the old theory is now. Yeah. The Earth-centered view of the universe bubbled astronomers who clung to it after a better theory was available. Similarly, the computer-centered view of the computer universe hobbled computer scientists to held on to it after the database-centered theory was available. It's tempting to trivialize the power of metaphors. To each of the early examples, the natural response is to say, well, of course the right metaphor is more useful. The other metaphors was wrong. That that's a natural reaction. It's simplistic. The history of science is a series of switches from the wrong metaphor to the right one. It's a series of changes from the worst metaphor to the better one, from the less inclusive to the more inclusive, from suggestive in one area to suggestive in another. In fact, many models that have been replaced by better models are still useful. Engineers still solve more engineering problems by using Newtonian dynamics, even though theoretically Newtonian dynamics have been supplanted by Einsteinian theory. Software development is a younger field than most of other sciences and is not yet mature enough to have a set of standard metaphors. Consequently, it has a profusion of complementary and conflicting metaphors. Some are better than others, some are worse, how well, and some are worse. How well you understand the metaphors determines how well you understand software development. Yeah. Mhm. Let's put them. Lose some Pomodoro, right? Why is my tracker focus? Okay, let's do continue this one. Let's just change this. Continue. Let's just do reading metaphors. I will also reading metaphors. I also need to do design. Then design patterns. And hopefully we can do some modeling actually. Binary Data Transfer Protocol, I already saw that. System design, haven't done it yet. Okay. Okay. How to use software metaphors? Let's this guy. A software metaphor is more like a searchlight than a roadmap. It doesn't tell you where to find the answer. It tells you how to look for it. A metaphor serves more as a heuristic than it does as an algorithm. An algorithm is a set of well-defined instructions for carrying out particular tasks. An algorithm is predictable, deterministic, and not a subject to chance. Okay, an algorithm tells you how you go from point A to point B with no detours, no side trips to point D and E and F, and no stopping to smell the roses or have a cup of joe. An heuristic is a technique that helps you look for the answer. It is results. Its results are subjects to chance because a heuristic tells you only how to look, not what to find. It doesn't tell you how to get directly from point A to point B. It might not even know where point A and point B are. In effect, a heuristic is an algorithm and in a clown suit. It is less predictable, it is more fun, and it comes without 30-day money back guarantee. Here is an algorithm for driving to someone's house. Okay, take a Highway 167 south to Puyallup, take the South Hill Mall, exit and drive 4.5 miles up to the hill. Turn right at the light by the grocery store, and then take the first left. Turn into the driveway of large tan house on the left at 714 North Cedar. Okay, just directions. And here is a heuristics for getting to someone's house. Find the last letter we mailed you. Drive to the town and the return address. When you get to town, ask someone where our house is. Everyone knows us. Someone will be glad to help you. If you can find anyone, call us from a public phone and we will come and get you. The difference between an algorithm and a heuristic is subtle, and the two terms overlap somewhat. For the purpose of this book, the main difference between the two is the level of indirection from the solution. An algorithm gives you the instructions directly, and a heuristics tell you how to discover the instructions for yourself, or at least where to look for them. Having directions that told you exactly how to solve your programming problems will certainly make programming easier and the results more predictable. But programming science isn't yet that advanced and might never be. The most challenging part of programming is conceptualizing the problem, and many errors in programming are conceptual errors. Because each program is conceptually unique, it is difficult or impossible to create a general set of directions that lead to a solution in every case. Thus, knowing how to approach problems in general is at least as valuable as knowing specific solutions for a specific problem. Mhm. So, how do you use software metaphors? Use them to give you insights into your programming problems and processes. Use them to help you think about your programming activities and to help you imagine better ways of doing things. You won't be able to look at the line of code and say that it violates one and of the metaphors described in this chapter. Over time, the person who uses metaphors to illuminate the software development process will be perceived as someone who has a better understanding of programming and produces better code faster than people who don't use them. Oof, this is bad, bro. This is a good one. La importancia de las metáforas en el desarrollo de software. Y la diferencia entre un algoritmo y heurística. La heurística en el desarrollo de software, como no es una guía dura, ¿no? De, de una receta a seguir para resolver un problema, sino es más que nada como una, una visión general de cómo podrías solucionarlo, ¿no? Aquí dice que es como un faro de luz. Ok. Eh, Dice cross-reference for detail of how to use heuristic in designer software. See design is heuristic processes in section 5.1. We will do that. We will get there. Actually, we're here. Mhm. So, common software metaphors. A confusing abundance of metaphors has grown up around software development. David Grice says writing software is science. Is a science, 1981. Dollard Knott says it's an art, 1988. Watts Humphrey says it's a process, 1989. Plodger and Ken Beck says it's like driving a car, although they draw nearly opposite conclusions. Plodger 1993 and 2000. Alistair Cockburn says it's a game. I like the game part and I like the art part. Eric Raymond says it's like a bazaar. Andy Hunt and Dave Thomas says it's like gardening. Paul Heckler says like it's like filming Snow White and Seven Dwarfs. Fred, I would like to know why. Fred Brook says that it's like farming, hunting werewolves, and or drowning with dinosaurs in a tar pit, which are the best metaphors. Oh man, I like the werewolves one. I like. Let's take a break. It's nice. I'm gonna take a quick break. It's 5 minutes. We're back. Dices que anda ahí. Mira, ya nomás te leo aquí. ¿Quieres aprender? ¿Quieres aprender? Solamente llegas aquí conmigo y puedes aprender sobre todo. Ahorita estamos aprendiendo sobre patrones de diseño. Estamos leyendo un libro escrito por Steve McConnell. Es un ganador de, del Jolt Award. Dos veces ganador del Jolt Award. Y estamos aprendiendo, leyendo sobre metáforas en el desarrollo de software. Muy bajito. A ver, ahora. A ver, ahora. Estaba muy bajo. Ahora probando. Estamos leyendo. A common software metaphor, a confusing abundance of metaphor has grown around software development. David Grice was writing software. Abundance of metaphor has grown around software development. David Grice was writing software. Cuando, bueno, a ver. Fabio, ¿cómo estás? ¿Cuánto tenemos de hablar? Hola, ahorita vamos a empezar. Bueno, vamos a continuar. Vamos a continuar con la lectura. Está bien interesante. Estamos hablando sobre metáforas en el desarrollo de software, la diferencia entre algoritmos, heurística, y vamos a integrar todo esto dentro de esta cuestión de diseño, ¿no? Diseño y construcción, trabajar con las clases, vamos a trabajar con rutinas, programación defensiva, procesos de programación con pseudocódigo. Pro, está bien, pro. Vamos a leer esto. Vamos a hacer una inmersión también a este libro y vamos a aplicar este conocimiento a nuestro programa. Vamos a modelar Crowley en base a este aprendizaje. Ya tenemos algunas ideas de cómo va a funcionar. Sabemos más o menos la lógica del negocio como tal. Debemos de crear una narrativa de ello. Al crear esa narrativa vamos a poder definir nuestras clases, nuestras relaciones, y ya le vamos a ir dando funcionalidad a cada uno de ellos. Pero de lo que se trata esto es simplemente de crear código limpio, que sea fácil de leer, que sea escalable, que lo podamos extender, que siga buenas prácticas y que, sobre todo, que no se convierta en basura, ¿no? Eso es lo que queremos. Entonces vamos a continuar en un momento. Denme 5 minutos. Ok, por té. A ver, ¿qué tenemos acá? relaciones. Aunque no estoy leyendo esto, a lo mejor se pueden confundir más. Code Complete es el que estoy leyendo. Este. ¿Qué edición es? Edición Second Edition. Está chido este O'Reilly, ¿eh? Te puedes hacer tu prueba gratuita y te va a dar acceso a este libro por 10 días, sin problema. Estamos de manera física a leerlo. Pero el otro de patrones de diseño no lo tenemos físico, así que lo vamos a leer directamente acá. Esto va a ser una lectura en español, está chido. Vamos a ver sobre estos los fundamentos de programación orientada a objetos, introducción, principios de diseño de software, los principios SOLID, muy importantes, single responsibility, el abierto cerrado, open and close, el least scope substitution, ¿no? De segregación de las interfaces, principio de inversión y dependencias, catálogo. Estos patrones de diseño están súper interesantes. Vamos a analizarlos, vamos a ver casos de uso de cada patrón y vamos a seleccionar el patrón que mejor se adapte a lo que estamos construyendo. ¿Ok? Pero si no sabemos y no conocemos nuestras herramientas, no podemos decidir cuál utilizar. Si solo sabes utilizar un martillo, siempre vas a usar ese martillo para todo, ¿no? ¿Cómo es el dicho? If you only have a hammer, ajá, sí. If you only have a hammer, everything looks like a nail. Si solo tienes un martillo, todo parece un clavo. Solamente tenemos un patrón de diseño o ninguno. Solamente conocemos estructuras de datos muy generales. Entonces, ¿qué pasa? Queremos utilizar la misma estrategia y las mismas metodologías y los patrones para todos los problemas. Y no es así. Debemos de adaptarlo. ¿Ok? Bueno. ver, bueno, vamos a continuar con esto. What's the calling? Desde que estábamos en cómo veían diferentes personas el software. Unos dicen que es un proceso, otros dicen que es arte, otros dicen que es ciencia. ¿Cuál te gusta? Dice, otros dicen que es como hacer farming, cazar lobos y ahogarse con dinosaurios en un pozo. Afo. Muy interesante ver por qué. Pero bueno. Software penmanship writing code. The most primitive metaphor for software development grows out of the expression writing code. The writing metaphor suggests that developing program is like writing a casual letter. You sit down with pen, ink, and paper and write it from start to finish. It doesn't require any formal planning and you figure out what you want to say as you go. Many ideas derive from the writing metaphor. John Bentley says you should be able to sit down by the fire with a glass of brandy, a good cigar, and your favorite hunting dog to enjoy a literate program. The way you will a good novel. Ah, that's nice. I like that. Like you will enjoy a literary program the way you will do with a good novel. Un buen código bien escrito es grato a la lectura, como una buena novela. Brian Cunningham and P.J. Plowger named their programming style book The Elements of Programming Style in 1978 after writing a style book The Elements of Style. Schunk and White, 2000 programmers often talk about program reliability. For an individual's work or for small-scale projects, the letter writing metaphor works adequately, but for the other purposes, it leaves the party early. It does not describe software development fully or adequately. No le puse que... Writing is usually a one-person activity, whereas a software project will most likely involve many people with many different responsibilities. When you finish writing a letter, you stuff it into an envelope and mail it. You can't change it anymore, and for all intents and purposes, it's complete. Software isn't as difficult to change. And it's hard. Oh, okay. And it's hardly even software isn't as difficult to change and is hardly even fully complete. As much as 90% of development effort on a typical software system comes after its initial release. With two-thirds being typical, this is a good thing. Like it says, as much as 90% of the development effort on a typical software system comes 90% after initial release. High premium is placed originally in software construction. Trying to create truly original work is often less effective than focusing on the reuse of design idea, code, and test cases from previous projects. In short, the writing metaphor implies a software development process that's too simple and rigid to be healthy. You have a nice graphic here. See? It says, plan to throw one away, you will anyhow.
If you plan to throw one away, you will throw away two. Okay. Unfortunately, the letter writing metaphor has been perpetuated by one of the most popular software books on the planet. Fred Brooks, the mythical man Mont, the mythical man Mont, Brooks 1995. Brooks says, "Plan to throw one away, you will anyhow." This conjures up an image of a pile of half-written drafts thrown into a wastebasket, as shown on Figure 2.1. The letter writing metaphor suggests that the software process relies on expensive trial and error rather than the careful planning and design. Mhm. You need to carefully plan and design. Planning to throw one away might be practical when you are writing how do you do to your aunt, but extending the metaphor of writing software to a plan to throw one away is poor advice for a software development. Where a major system already costs as much as 10-story office building or an ocean liner, it is easy to grab the brass ring if you can afford to sit on your favorite wooden pony for an unlimited number of spins around the carousel. The trick is to get it the first time around or to take several chances when they are cheapest. Other metaphors very illuminate ways of attaining such goals. Mhm. Then we have software farming, growing a system. In contrast to the rigid writing metaphor, some software developers say you should envision creating software as something like planting seeds and growing crops. You design a piece, code a piece, ooh, you design a piece, code a piece, test a piece, and add it to the system a little bit at a time. Design, code, test. Design, code, test. Plan, design, and test. You minimize the trouble you can get into at any one time. Sometimes, ah, sometimes a good technique is described with a bad metaphor in such cases. Try to keep the technique and come up with a better metaphor in this case. The incremental technique is valuable, but the farming metaphor is terrible. Sometimes a good technique is described with a bad metaphor. In such cases, try to keep the technique and come up with a better metaphor. In this case, the incremental technique is valuable, but the farming metaphor is terrible. The idea of doing a little bit at a time might bear some resemblance the way crops grow, but the farming analogy is weak and uninformative, and is easy to replace with its better metaphor described in the following sections. It is hard to extend the farming metaphor beyond the simple idea of doing things a little bit of a time. If you buy into the farming metaphor, imagine an inferior to two, you might find yourself talking about fertilizing the system, planting, tidying and the detailed design, increasing code yields through effective land management, and harvesting the code itself. You will talk about rotating in a row of C++ instead of barely letting the land rest of the years to increase the supply of nitrogen in the hard disk. The weakness in the software farming metaphor is is suggestion that you don't have any direct control over how the software develops. You plant the code seed in the spring, farmer's almanac, and the grape coming willing, you will have a bumper crop code in the fall. It is hard to extend the farming metaphor to software development appropriately. Software oyster farming system approach. Sometimes people talk about growing software when they really mean software creation. That the two metaphors are closely related. The two metaphors are closely related, but software creation is the more insightful image. Creation, a creation, in case you don't have the dictionary handy, means any growth or increase in size. Any growth or increase in size by a gradual externalization or inclusion. Accretion describes the way an oyster makes a pearl by gradually adding small amounts of calcium carbonate. In geology, accretion means a slow addition to land by the deposit of waterborne sediment. In legal terms, accretion means an increase of land along the shores of a body of water or by the deposit of waterborne sediment. For detail of how to apply incremental strategies to system integration, see section 29.2, integration frequency. Okay, this doesn't mean that you have to learn how to make code out of waterborne sediments. It means that you have to learn how to add to your software systems a small amount of the time. Add to the software system a small amount of time. Incremental designing, building, and testing are some of the most powerful software development concepts available. In incremental development, you first make the simplest possible version of the system that will run. Okay, okay. It doesn't have to accept realistic imp it doesn't have to perform realistic manipulation of data. Okay. It doesn't have. It doesn't have to produce realistic output. It just has to be a skeleton. Strong enough to hold a real system and its development. It might call dummy classes. Mhm. Of each of the basic functions you have identified. This basic beginning is like the oyster's beginning, a pearl with a small grain of sand. It's a pearl within the oyster, right? It's cool. After you have formed the skeleton, little by little, you lay on the muscle and the skin. You showing off the dummy classes to real classes. Mhm. Instead of having your program pretend to accept input, you drop in code that accepts your input. Mhm. Instead of having your program pretend to produce an input, you drop in code to produce a real input output. You add a little bit of code at a time until you have a fully working system. The anecdotal evidence in favor of this approach is impressive. Fred Brooks, who is in 1975 advised building one of the throwaways, said that nothing in the decade after he wrote his landmark book, The Mythical Man Mound, so radically changed his own practice or its effectiveness as incremental development, 1995. Tom Glebe made that made the same point in his breakthrough book, Principles of Software Engineering Management, which introduced evolutionary delivery and laid and laid the groundwork for much of today's agile programming approach. Numerous current methodologies are based on this idea. Beck 2000, Cockburn 2002, Highsmith 2002, Rayfair 2002, and Martin 2003, and Larman 2004. As a metaphor, the strength of an incremental metaphor is that it does not overpromise. It is harder than the farming metaphor to extend inappropriately. The image of an oyster forming a pearl is a good way of visualizing incremental development or accretion. Continuemos. Software construction, building software. The image of building software is more useful than that of writing or growing software. It's compatible with the idea of software creation and provides more detailed guidance. Building software implies various stages, planning, preparation, execution, and that vary in kind and degree depending on what's being built. When you explore the metaphor, you find any other parallels. Building 4-foot tower requires a steady hand, a level surface, and 10 undamaged beer cans. Building tower 10 times that size doesn't merely require 100 times as many beer cans. It requires different kind of plannings and constructions together. Construction all together. If you are building a simple structure, a doghouse, say, you can drive to the lumber store and buy some wood and nails. By the end of the afternoon, you will have a new house for Fido. If you forget to provide for a door, as shown in figure 203, Lord, or make some of other mistake, it's not a big problem. You can fix it or even start over from the beginning. All you have wasted is part of an afternoon. This loose approach is appropriate for small software projects. If you use the wrong design for 1000 lines of code, you can refactor or start over completely without losing much. The penalty for a mistake on a simple structure is only a little time and maybe some embarrassment. If you are building a house, the building process is more complicated, and so are the consequences of poor design. First, you have to design what kind of house you want to build. First, decide what kind of house you want to build. Analogous in the software development to problem definition. Then you and an architect have to come up with a general design and get it approved. This is similar. This is similar. What kind? General design. This is similar to software architectural design. You draw a detailed blueprint, mhm, and hire a contractor. This is similar to This is similar to details over design. You prepare the building site, lay a foundation, frame the house, put a siding and roof on it, and plumb and wire it. This is similar to software construction. When most of the house is done, the landscaper, painters, and decorators comes in to make the best of your property and the home you have built. This is similar to software optimization. Throughout the process, various inspectors come to check the site, foundation, frame, wiring, and other inspectables. This is a similar to software reviews and inspection. Greater complexity and size imply greater consequences in both activities. In building a house, materials are somehow expensive, but the main expense is labor. Ripping out a wall and moving it 6 inches is expensive not because you waste a lot of nails, but because you have to pay the people for the extra time it takes to move the wall. You have to make the design as good as possible as suggested by figure 2-4 so that you don't waste time fixing mistakes that could have been avoided. In building a software products, materials are even less expensive, but labor costs just as much. Changing a report format is just as expensive as moving a wall in a house because the main cost component in both cases is people's time. Okay. More complicated structures require more careful planning. Mhm. What other parallels do to do that two activities share? What other parallels do that two activities share? In building a house, you won't try to build things you can buy already built. You will buy a washer or a dryer. You will buy a washer or a dryer, a dishwasher, a refrigerator, or a freezer. Because you are a mechanical wizard, you won't consider building them yourself. You will also buy prefabricated cabinets, counters, windows, doors, and bathroom fixtures. If you are building a software system, you will do the same thing. You will make extensive use of high-level language features rather than writing your own operating system level code. You may also use pre-built libraries or of container classes, scientific functions, user interfaces classes, and database manipulation classes. In, it generally doesn't make sense to code things you can buy ready-made. If you are building a fancy house with first-class furnishing, however, you might have your cabinets custom made. You may have a dishwasher, refrigerator, and freezer built in to look like the rest of your cabinets. You may have a window custom made in unusual shapes and sizes. This customization has parallels in software development. If you are building a first-class software product, you may build your own scientific functions for better speed or accuracy. You may build your own container classes, user interfaces classes, and databases classes to give your system a seamless, perfectly consistent look and feel. Both building construction and software construction benefits from appropriate levels of planning. If you build software in the wrong order, it's hard to code, hard to test, and hard to debug. It can take longer to complete, or the project can fall apart because everyone's work is too complex and therefore too confusing when it's all combined. Careful planning doesn't necessarily mean exhaustive planning. Mhm. This is important. Or over planning. You can plan out the structural supports and decide later, plan structural support, and decide later whether to put in hardwood floors or carpeting, what color to paint the walls, what roofing materials to use, and so on. A well-planned project improves your ability to change your mind later about details. The more experience you have with this kind of software you are building, the more details you can take for granted. You just want to be sure that you plan enough. You just need to be sure that you plan enough so that lack of planning doesn't create major problems later. The construction analogy also helps explaining why different software projects benefit from different development approaches. In building, you will use different levels of planning, design, and quality assurance if you are building a warehouse, or a toolshed stand if you are building a medical center or a nuclear reactor. You will use still different approaches for building a school, a skyscraper, or a three-bedroom home. Likewise, in software, you might generally use flexible, lightweight development approaches, but sometimes you will need rigid, heavyweight approaches to achieve safety goals and other goals. Making changes in the software brings up another parallel with building construction. Making changes in software parallel. To move a wall 6 inches costs more if the wall is load-bearing than if it's merely partitioned between rooms. Similarly, making structural changes in a program costs more than adding or deleting peripheral features. Ese nota. Okay.
Okay. Making changes in the software brings another parallel with building construction. With building construction, to move a wall 6 inches costs more if the wall is load bearing than it's merely a partition between rooms. Similarly, taking structural changes in a program costs more than adding or deleting peripheral features. Finally, the construction analogy provides insight into extremely large software projects because the penalty for failure in an extremely large structure is severe. The structure has to be over-engineered. Builders make and inspect their plans carefully. They build in margins of safety. It's better to pay 10% more for stronger material than to have two skyscraper file over. Yeah. A great deal of attention is paid to timing. When the Empire State Building was built, each delivery truck had 15 minutes margin in which to make its delivery. If a truck wasn't in place at the right time, the whole project was delayed. Likewise, for extremely large software projects, planning of higher order is needed than for projects that are very large. Capper-Jones report that a software system with 1 million lines of code requires an average of 69 kind of documentation. 1998. The requirement specifications for such systems will typically be about 4K or 4 to 5K page long. The design documentation can easily be 2 or 3 times as extensive as the requirements. It is unlikely that an individual will be able to understand the complete design for a project of this size or even read it. A greater degree of preparation is appropriate. For some good comments about extending the construction metaphor, see what support the roof. Start 2003. Okay. So we build software projects comparable in economic size to the Empire State Building, and technical and managerial control of similar stature are needed. The building construction metaphor could be extended in a variety of other directions, which is why the metaphor is so powerful. Many terms common in software development derive from the building metaphors: software architecture, scaffolding, construction, foundation classes, and tearing code apart. You will probably hear more. So, applying software techniques, the intellectual toolbox. People who are effective at developing high quality software have spent years accumulating dozens of techniques, tricks, and magic incantations. The techniques are not rules, they are analytical tools. They are analytical tools. A good craftsman knows the right tool for the job and knows how to use it correctly. This is Tasso. A good craftsman knows the right tool for the job and knows how to use it correctly. Programmers do too. The more you learn about programming, the more you fill your mental toolbox with analytical tools and the knowledge of when to use them and how to use them correctly. For details on selecting and combining methods in design, see section 5.3, Design Building Blocks, Heuristics. Okay. In software, consultants sometimes tell you to buy into certain software development methods to the exclusion of other methods. That's unfortunate because if you buy into any single methodology 100%, you will see the whole war in terms of that methodology. If you buy into any methodology 100%,
You will see the whole world in terms of that methodology. In some instances, you will miss opportunities to use other methods better suited to your current problem. The toolbox metaphor helps to keep all the methods, techniques, and tips ready ready for use when appropriate. Like combining metaphors. Because metaphors are heuristic rather than algorithmics, metaphors are heuristic rather than algorithmic, they are not mutually exclusive. You can use both the creation and the construction metaphors. You can use writing if you want to, and you can combine writing with driving. Hunting for werewolves or drowning in the tar pit with dinosaurs, use whatever metaphors or combination of metaphors stimulates your own thinking or communicates well with others on your team. Using metaphors is a fussy business. You have to extend them to benefit from the heuristics insight they provide. But if you extend them too far or in the wrong direction, they will mislead you. If you extend them too far or in the wrong direction, they will mislead you. Just as you can misuse any powerful tool, you can misuse a metaphor, but their power makes them a valuable part of your intellectual toolbox. Okay? Additional resources among general books of metaphors, models, and paradigms. The touchstone book is Thomas Kuhn. Thomas Kuhn. In the Structure of Scientific Revolution, third edition, Chicago. The University of Chicago Press, 1996, Kuhn's book of how scientific theories emerge, evolve, and succumb to other theories in a Darwinian cycle set the philosophy of science on its ear when it was first published in 1962. It is clear and short and is loaded with interesting examples of the rise and fall of metaphors, models, and paradigms in science. Floyd, Robert W. The Paradigms of Programming. 1978, Turing Award Lectures, Communication. Okay. Key points. Metaphors are heuristics, not algorithms. As such, they tend to be little sloppy. So these are the key points, takeaways. Metaphors help you understand the software development process by relating it to other activities you already know about. Okay? Some metaphors are better than others. This is good. Treating software construction as similar to building construction suggests that careful preparation is needed and illuminates the difference between large and small projects. Thinking of software development practices as tools in an intellectual toolbox suggests further that every programmer has many tools and that no single tool is right for every job. No single tool is right for every job. Choosing the right tool for each problem is one key to begin effective programming. Right? Metaphors are not mutually exclusive. Use a combination of metaphors that works best for you. Hmm? Okay. Measure twice. Prerequisite. Prerequisites. Compelling, compelling and foolproof argument. Okay. Determine what kind of software you are working on. Capers Jones, chief scientist at Software Productivity Research, summarized 20 years of software research by pointing out that he and his colleagues have seen 40 different methods for gathering requirements, 50 variation in working on software designs, and 30 kind of testing apply project to more than 70 different programming languages. Different kind, damn dude. Like 40 met 40 40 30 and 700 language test recs. Different kind of software projects call for different balances between preparation and construction. Every project is unique, but projects do tend to fall into general development styles. Table 3 in 2 shows three of the most common kind of projects and lists the practices that typically best suit to each kind of project. Typical good practices for three common kind of software projects: business systems, mission critical systems, embedded life critical systems. So business systems, we have internet sites, intranet sites, inventory management, games, management, information systems, payroll systems, typical applications, and life cycle models with agile development, which is stream programming, Scrum, time box development, so evolutionary prototyping. So mission critical, okay, so systems, mission critical systems, embedded software, games, internet site, packages software, software tools, web services, stage delivery, evolutionary delivery, spiral development. Embedded life critical systems, avionic system software, embedded systems, medical devices, operating systems, package software, stage delivery, spiral development, evolution delivery, stage development, spiral development, stage delivery, delivery, stage delivery. Okay. Planning and management, incremental project planning, as need test and QA planning, informal change control, requirements, informal requirements application, design and coding. Okay, life is one. Okay, business systems. So I mention critical systems. Planning management, incremental project planning, as needed test QA planning. This is the planning and management for the business systems. Incremental project planning, as needed test and QA planning, informal change control. Requirements, informal requirements specification, design, design and coding are combined. Construction, pair programming or individual coding, informal check-in procedure or no check-in procedure. Testing and QA, developer test their own code, test first development, little or no testing by a separate test group. And deployment is formal deployment procedure. For uh, for mission critical systems, um, we have basic pre-planning and management. We have basic upfront planning. We have basic test planning as needed QA planning, formal change control. Requirements will be semi-formal requirement specification, as needed requirements, and design will be architectural design, informal detail design, as needed design. Construction will be pair programming, informal checking procedure, and as needed code reviews. Testing in QA, developer tests their own code, test for development, separate testing group, and deployment will be a formal deployment procedure. So for embedded life critical systems will be any kind of aviation, medical, uh, operating system, packages, software. Uh, we will have extensive upfront planning. We will do extensive planning, test planning. We will do extensive QA planning, rigorous change control. We do formal requirement specifications. We do formal requirement inspections. In design, we will do architectural design. We will do formal architecture inspections. We will do formal detail design. We will do formal detail design inspections. We will also do over construction. We will do pair programming on individual coding, formal shaking procedure, and also we will add in formal code inspections. For testing and QA, we have developers test their own code, test first development and separate testing group with a separate QA group, and development finally we have formal deployment procedures. On real projects, you find infinite variations on the three themes presented in this table. However, the generalities in the tables are illuminating business and system projects to benefit from highly iterative approaches in which planning requirements and architecture are interrelated with construction system testing and quality assurance activities. Life critical systems tend to require more sequential approaches. Requirement stability is part of what's needed to ensure ultra high levels of reliability. Okay, iterative approach. Some writers have asserted that projects that use iterative techniques don't need to focus on prerequisites much at all, but that point of view is misinformed. Iterative approaches tend to reduce the impact of inadequate upstream work, but they don't eliminate it. Consider the example shown in Table 3.3 of projects that don't focus on prerequisites. One project is conducted sequentially and relies solely on testing to discover defects. The other is conducted iteratively and discovers defects at its progresses. The first approach delays most defect corrections work to the end of the project, making the cost higher, as noted in Table 3.1, and the iterative approach absorbs reward piecemeal over the course of the project, which makes the total cost lower. The data in this table and the next is for purposes of illustration only, but the relative costs of the two general approaches are well supported by the research described early in this chapter. Table 3.3 Effect of skipping prerequisites on sequentials and iterative projects. Approach 1 Sequential approach without prerequisites. Approach 2 Iterative approach without prerequisites. Sequential and iterative. So project completion status, cost of work, cost of reward, cost of work, cost of reward. So project status when it's 20%, we have 100K for cost of work, we have zero cost of reward, we have 1K, 100K cost of work. Okay, this is okay. Let's put it like this. So we're doing sequential. There is no cost of reward in any of the phases from 20, 40, 60, 80, 100%. We have cost of work for each of those blows. They are 100K percent. They are 100K. So in approach 2, we have an iterative approach without prerequisite, which is the cost of work will be $100,000 and the cost of reward will be $75,000. So the end of the project rework on that sequential approach is the cost of work and reward will be 500K. Total of $500,000. We have zero reward. That will be a grand total of 1 million. In the other hand, we do have mhm, 0, 0, reward 0, and a prior reward 0. Okay, gotcha. So you have a sequential with no reward at the end of the project you are going to spend 5K. Okay. The iterative project that abbreviates or eliminates prerequisites will differ in two ways from the sequential project that does the same thing. First, average defect correction costs will be lower because defects will tend to be detected closer to the time they were inserted into the software. However, the defects will still be detected late in each iteration, and correcting them will require part of the software to be redesigned, recoded, and retested, which makes the defect correction cost higher than it needs to be. Okay, let's jump into the modeling part. Part 2, creating high quality code. In this part, we will learn in chapter 5 the design in construction. Then we will learn about working in classes. There are also other topics like high quality routines and defensive programming, the pseudocode programming process. We will be reading through chapter 5 and chapter 6. Okay, designing construction. Contents 5.1 Design challenges. 5.2 Key design concepts. 5.3 Design building blocks, heuristics. 5.4 Design practice. Okay. 5.5 Comments on popular methodologies. And related topics, we have software architecture in section 3.5. We have working classes on chapter 6, which are characteristics in high quality routines in chapter 7, defensive programming in chapter 8, factor in chapter 24, how program size affect constructions in chapter 27. Okay, some people might argue that design isn't really a construction activity. This is where we started the first time of the stream. Then we moved back. We just went back to learn more about. We'll get there. Okay, so some people is here for detail on the different level for mm, formality required on the version small projects. Oh no, this is not the one. It should be other way. Okay. Some people might argue that design isn't really a construction activity, but on small projects, many activities are thought as a construction, often including design. On some larger projects, a formal architecture might address only the system level issues, and much design work might intentionally be left for construction. On other large projects, the design might be intended to be detailed enough for coding to be fairly mechanical, but design is rarely that complete. The programmer usually design part of the program officially or otherwise. On small informal projects, a lot of design is done while the programmer sits at the keyboard. Design might be just writing a class interface in pseudocode before writing the details. It might be drawing diagrams of a few class relationships before coding them. It might be asking another programmer which design pattern seems like a better choice. This is programmer with design pattern seems like a better choice, drawing diagrams, a few class relationships before coding them. Regardless of how it's done, small projects benefit from a careful design just as larger projects do. and recognizing design as an explicit activity maximize the benefit you will receive from it. Design is a huge topic, so only a few aspects of it are considered in this chapter. A large part of good class or routine design is determined by the system architecture. So be sure that the architecture prerequisite discussed in section 3.5 has been satisfied. Even more design work is done at the level of individual classes and routine described in chapter 6, working with classes, and chapter 7, high quality routines. If you are already familiar with software design topics, you might want to just hit the highlights in the section about design challenges in section 5.1 and key heuristics in section 5.3. So let's check. I think we'll need to go to 3.5 also, 3.5, which is, there you go. This one. The cover leak. Architecture. Architecture. Okay. Architecture prerequisite. Software architecture is the high-level part of software design. High-level part of software design. The frame that holds the more detailed part of the design is a frame. Buskman et al. 1996, Fowler 1202, Bas Clemens, Kasman 1203, Clemens et al. '03. Architecture is also known as system architecture for high-level design and top-level design. Typically, the architecture is described in a single document referred to as the architecture specification. Doc. This is what we're going to create. The architecture specification. Some people make a distinction between architecture and high-level design. Architecture refers to design constraints that apply system-wide, whereas high-level design refers to design constraints that apply at a subsystems system-wide or multiple class level, but not necessarily system-wide. Because this book is about construction, this selection doesn't tell you how to develop a software architecture. It focuses on how to determine the quality of an existing architecture. Because architecture is one step closer to construction than requirements. However, the discussion of architecture is more detailed than the discussion of requirements. Let's see if they have. Pero Those functional requirements are all inputs to the system specified, including their source, accuracy, range of values, and frequency. Area are all the outputs from the system specified, including the destination, accuracy, range of values, frequency, and format. Are all output format specified for web user report and so on? Okay, questions, man. Stupid. Okay. Hmm. Are all output format specific with preface? Are all external hardware and software interfaces specified? Are all external communication interfaces specified, including handshaking, error checking, and communication protocols? Are all the tasks the user wants to perform specified? Is the data used in each task and the data resulting from each task specified? Specific non-functional quality requirements is the expected response time from the user point of view specified for all necessary operations? Are other timing considerations specified such as processing time, data transfer rate, and systems throughput? Is this level of security specified? Is the reliability specified, including the consequences of software failure, the vital information that needs to be protected from failure, and the strategy for error detection and recovery? Are minimum machine memory and free disk space specified? Is the maintainability of the system specified, including its ability to adapt to change in specific functionality, changes in the operating environment, and changes in its interfaces with other software? Is the definition of success included? Failure? Requirements quality. Are the requirements written in the user language? Do the users think so? Does each requirement avoid conflict with other requirements? Are acceptable trade-offs between competing attributes specified? For example, between robustness and correctness? Do the requirements avoid specifying the design? Are the requirements at a fairly consistent level of detail? Should any requirement be specified in more detail? Should any requirement be specified in less detail? Are the requirements clear enough to be turned over to an independent group for construction and still be understood? Do the developers think so? Is, is each item relevant to the problem and its solution? Can each item be traced to its origin in the problem environment? Is each requirement testable? Will it be possible for independent testing determine whether each requirement has been satisfied? Are there possible changes to requirements specified, including the least likelihood of each change? Requirement completeness. Where information isn't available before development begins, are the areas of incompleteness specified? Are the requirements complete in the sense that if the product satisfies every requirement, it will be acceptable? Are you comfortable with all the requirements? Have you eliminated requirements that are impossible to implement and include so just to appease the customer or your boss? Okay. Problem definition, requirements, architecture, construction, system testing, and future improvements. Mhm. So problem definition. The problem is building on the foundation of the rest of the programming process. If the box is the boundary of constraint and conditions, then the trick is to find the box. If the box is the boundary, don't think outside the box. Find the box. The first prerequisite you will need to fulfill before beginning construction is a clear statement of the problem that the system is supposed to solve. Okay? So, this is sometimes called product vision statement, mission statement, or product definition. Here is called problem definition. Since this book is about construction, this section doesn't tell you how to write problem definitions. It tells you how to recognize whether one has been written at all and whether the one that is written will form a good foundation for construction. A problem definition defines what the problem is without any reference to possible solutions. It is a simple statement, maybe 1 or 2 pages, and it should sound like a problem. The statement, we can keep up with orders for the gigatron, right? Sounds like a problem and it's good problem definition. The statement, we need to optimize our automated data entry system to keep up with orders for gigatron, is a poor problem definition. It doesn't sound like a problem, it sounds like a solution. As shown in figure 3034, problem definition comes before detailed requirement work, which is more in-depth investigation of the problem. Okay. In-depth. In-depth. Aquí vamos a ser más como. So the problem definition lays the foundation for the rest of the programming process. The problem definition should be in user language, and the problem should be described from the user's point of view. It usually should not be stated in technical computer terms. The best solution might not be a computer program. Suppose that you need a report that shows your annual profit. You already have computerized reports that show quarterly profits. If you are locked into the programmer's mindset, you will reason that adding an annual report to a system that already does quarterly reports should be easy. Then you will pay a programmer to write at the book a time-consuming program that calculates annual profit. If you are not locked into the programmer's mindset, you will pay your secretary to create the annual figures by taking 1 minute to add up the quarterly figures on a pocket calculator. Mhm. The exception to this rule applies when the problem is with the computer. Compile times are too slow or the programming tools are buggy. Then it's appropriate to state the problem in the computer or programmer terms. Figure 3.5 suggests without a good problem definition, you might put effort into solving the wrong problem. It is fine to hope that once your customer has accepted requirements documents, no changes will be needed on a typical project. However, the customers can reliably describe what is needed before the code is written. The problem isn't that the customers are a lower life form. Just as the more you work with the project, the better you understand it. The more they work with it, the better they understand it. The development process helps. This is just so distracting. How much change is typical? Studies at IBM and other companies have found that the average project experiences about a 25% change in requirements during the development. Boom 1981 joins 1994 joins 2000, which accounts for 70 to 85% of the rework on a typical project. Maybe you think the Pontiac Aztek was the greatest car ever made, belong to the Flat Earth Society, and make a pilgrimage to the alien landing site at Roswell, New Mexico, every 4 years. If you do, go ahead and believe the requirements won't change on your projects. If, on the other hand, you have to stop believing in Santa Claus and the Tooth Fairy, or at least have stopped admitting it, you can take several steps to minimize the impact of requirements change. Handling requirements change during constructions. Here are several things you can do to make the best of changing requirements during construction. Use a requirements checklist at the end of the sections to assess the quality of your requirements. If your requirements aren't good enough, stop work, back up, and make them right before you proceed. Sure, it feels like you are getting behind if you stop coding at this stage, but if you are driving from Chicago to Los Angeles, it is a waste of time to stop and look at the roadmap when you see the sign for New York. Isn't a waste of time to stop and look at the roadmap when you see signs for New York? No, if you are not heading to the right direction, stop and check your course. Make sure everyone knows the cause of requirement changes. Clients get excited when they think of a new feature. In their excitement, their blood thins and runs to their medulla oblongata, and they become giddy, forgetting all the meetings you had to discuss requirements, the signing ceremony, and the completed requirements documents. The easy way to handle such feature intoxicated people is to say, gee, that sounds like a great idea. Since it's not in the requirements documents, it will work up a revised schedule and cost estimate so that you can decide whether you want to do it now or later. The worst schedule and cost are more sobering than coffee and cold shower, and many must-haves will quickly turn into nice-to-haves. Hell yeah, man. Schedule, cost. I will cover a revision schedule and cost estimate so you can decide. If your organization is insensitive to the importance of doing requirement first, point out that changes at requirements time are much cheaper than changes later. Use this chapter utterly compelling and foolproof arguments for doing prerequisites before construction. Okay, for details on handling changes to design and code, see section 28.2 configuration management. For details on iterative development approaches, see it in section 5.4 and 29.3 incremental integration and strategies. For detail on development approaches that support flexible requirements, see Rapid Development from Macaulay 1996, and for detail on the reference between formal and informal projects, often caused by difference in project size, the chapter How to Program Size Affects Construction. Okay, so set up a change control procedure. If your client's excitement persists, consider establishing a formal change control board. To review such proposed changes, it's all right for customers to change their mind and to realize that they need more capabilities. The problem is they're suggesting changes so frequently that you can't keep up. Having a built-in procedure for controlling changes makes everyone happy. You are happy because you know that you will have to work with changes only on specific times. Then your customers are happy because they know that you have a plan for handling their input. Use development approaches that accommodate changes. Some development approaches maximize durability to respond to changing requirements. An evolutionary prototyping approach use development approaches that accommodate changes. Some development approaches maximize durability to respond to changing requirements. An evolutionary prototyping approach helps you explore a system's requirement before you send your forces in to build it. Evolutionary delivery is an approach that delivers the system in stages. You can build a little, get a little feedback from your users, adjust your design a little, make a few changes, and build a little more. The key is using short development cycles so that you can respond to users quickly. Break, night, break to reflect, walk around, stretch.
Dump the project. If the requirements are especially bad or volatile, and no one of the suggestions above are workable, cancel the project. Even if you can rely, cancel the project. Think about what it would be like to cancel it. Think about how much work it would have to get before you would cancel it. If there is a case in which you will dump it, at least ask yourself how much difference there is between your case and that case. Keep an eye on the business case for the project. Many requirements issues disappear before your eyes when you refer back to the business reason for doing the project. Requirements that seems like good idea when considered as features can seem like terrible ideas when you evaluate the incremental business value. Programmers who remember to consider the business impact of their decisions are worth their weight in gold. Although I will be happy to receive my commission for this advice in cash. Oh yeah. Okay. So they have a requirement list about this. Fine. It's fine. Architecture, the architecture specification. So here, let's do problem statement. Let's do requirements. Let's do architecture. Uh, Construction and testing. Okay. ¿Cómo se llama este software definition document? Software design documentation and description of the software. Software design document. Que no estuviera mal hacerlo. Entro al menú Visual Studio de una vez con Markdown. Acá hay varias cosas. A lo mejor aquí no vamos a hacer nada de nada. No existe los resultados. Let's see. Requirements. Requirements. Requirements describe. Okay, in penalty for failing to define the problem is that you can waste a lot of time solving the wrong problem. This is
double-barreled penalty because you also don't solve the right problem. Requirements prerequisite. Requirements describe in detail what a software system is supposed to do, and they are the first step towards solution. The requirements activity is also known as requirements development, requirement analysis, requirement definition, software requirements, specifications, functional specification, specs. Mhm. Why have official requirements? An explicit set of requirements is important for several reasons. Explicit requirements help you to ensure that the user rather than the programmer drive the system functionality. The user rather than the programmer drive the system functionality. If the requirements are explicit, the user can review them and agree to them. If they are not, the programmer usually ends up making requirements decisions during the programming. Explicit requirements keep you from guessing what the user wants. Explicit requirements also helps to avoid arguments. You decide on the scope of the system before beginning on programming. This is important. You decide on the scope of the system before you begin programming. If you have a disagreement with another programmer about what the program is supposed to do, you can resolve it by looking at the written requirements. Paying attention to requirements helps to minimize changes to a system after development begins. If you find a coding error during coding, you change a few lines of code and work goes on. If you find a requirement error during the coding, you have to alter design to meet the changes requirement. You might also throw away part of the old design. And because it has no to accommodate code that is already written, the new design will take longer than it would have in the first place. You also have to discard code and test cases affected by the requirement changes and write new code and test cases. Even code that's otherwise unaffected must be retested so that you can be sure that changes in other areas haven't introduced any errors. As Table 3.1 reported, data from numerous organizations indicates that on large projects as an error in requirements detected during the architecture stage is typically 3 times as expensive to correct and it would be it if were detected during the requirements stage. If detected during the coding, it is 5-10 times as expensive. During system tests, 10 times. And post-release whooping to 10 to 100 times as expensive as it would be if it were detected during requirements development. On smaller projects with lower administrative costs, the multiplier post-release is closer to 5, 10 than 100. Boehm and Turner 2004. In either case, it isn't money you want to have taken out of your salary. Specifying requirements adequately is a key to a project's success, perhaps even more important than effective construction techniques. See Figure 3.6. Construction techniques. Without good requirements, you can have the right general problem, but miss the mark on a specific aspect of the problem. Oh, I didn't start. Okay. Many good books have been written about how specific requirements well how to specify requirements well. Consequently, the next few sections don't tell you how to do a good job of specifying requirements. They tell you how to determine whether the requirements have been done well and how to make the best of the requirement you have. So do you have this checklist? We don't have like a like a mental model of how to build an actual uh, requirements documents or a problem definition. Like we don't have we have just a way of evaluate it. Stable requirements are the holy grail of software development. With stable requirements, a project can proceed with architecture to design, to coding, to testing in a way that's orderly, predictable, and calm. This is software heaven. You have predictable expenses, and you never have to worry about feature costing 100 times as much to implement as it would otherwise because your user didn't think of it until you were finishing the work. It is fine to hope that once your customer has accepted the requirements document, no changes will be needed on typical project. However, we already did this. Okay, we finish this. Let's finish this too. Do do do. do. We'll read about. Okay, metaphors for research understanding of software development. How to use software metaphors. How to use the common software. We talk about common software metaphors. We read about that. Software penmanship, code, software farming, growing a system, software oyster farming, system creation, software construction, building software. Uh, what else? We have a lot of graph, we have a lot of good tips, more complicated structures, additional resources, key points about metaphors. We didn't read about measure twice, good ones. We didn't read about this. It's important to have prerequisites. We know about that. Logic and then do this. We did we did read about determine the kind of software we are working on, knowing that the kind of software between business systems, mission critical systems, embedded life critical systems. It's a good reading session. Approach one for this is the approaches effects on prerequisites, the cost of non having prerequisites of different approaches. Yeah, like yeah, sequential and iterative projects. Mhm. Well, we review about the problem definition prerequisite. We know that that's the first thing we need to do after requirements, architecture, construction, system testing, and after that we do the future improvements. The importance of having these as official requirements. We have uh, the meat of stable requirements, which is a heaven and will cost not cost a lot. We will handling requirements during construction. We also check out setup change control procedure, use development approaches that accommodate changes, dump the project, keep the eye on the business case for the project. We review a checklist for requirements, for specific functional requirements, specific not functional quality requirements, requirements quality, architecture prerequisites. We know about the document, which is called architecture specification. We are reading through this right now. Typical architecture. We need to go through the. We need to go through this chapter 3.5 for architecture prerequisite. We will. Okay, this looks good. Okay, so the idea is to know how to design in construction, have a good understanding of this, and how to use working classes. So to fully understand it, we have gone through a lot of other info, but we still need to go through the architectural prerequisite right here. Yeah. So yeah, the documental specification. Because the book is about construction, this section doesn't tell you how to develop a good architecture. It's focused on how to determine the quality of an existing architecture, because architecture is one step closer to construction than requirements. However, the discussion of architecture is more detailed than the discussion of requirements. Why have architecture as a prerequisite? Because the quality of architecture determines the conceptual integrity of the system, that in turn determines the ultimate quality of the system. A well a well thought out architecture provides the structure needed to maintain a system conceptual integrity from the top levels down to the bottom. It provides guidance to programmers at a level of detail appropriate to the skill of the programmers and to the job at hand. It partitions the work so that multiple developers or multiple development teams can work independently. Good architecture makes construction easy, bad architecture makes construction almost impossible. Figure 7.3 illustrates another problem with bad architecture. Figure 7.3. Without a good software architecture, you may have the right problem, but the wrong solution. It might be impossible to have a successful construct. Mhm. Architectural changes are expensive to make during construction or later. The time needed to fix an error in a software architecture in on the same order as that needed to fix a requirement error, that is more than that needed to fix a coding error. Basili and Perricone 1984, Willis 1998. Architecture changes are like requirement changes in that simply small changes can be far-reaching. Whether the architectural changes arise from the need to fix error or the need to make improvements, the earlier you can identify the changes, the better. Changes are like so, cross-reference. For detail on lower-level program design, check chapter 5 through 9. So many components are common to good system architectures. If you are building the whole system yourself, this is good, you will work on architecture will overlap your work on the more detailed design. Your work on the architecture will overlap your work on the more detailed design. In such a case, you should at least think about each architectural component. If you are working on a system that was architected by someone else, you should be able to find the important component without a bloodhound, a deer stalker cap, and a magnifying glass. In either case, here are the architectural components to consider. Number one, program organization. If you can explain, if you can't explain something to a 6-year-old, you really don't understand it yourself. Albert Einstein. Program organization. A system architecture first need an overview that describes the system in broad terms. Without such an overview, you will have a hard time building a coherent picture from 1,000 details or even a dozen of individual classes. If the system were if the system were a little 12-piece jigsaw puzzle, your 1-year-old could solve it between spoonfuls of strained asparagus. A puzzle of 12 subsystems is harder to put together, and if you can't put it together, you won't understand how a class you are developing contributes to a system. You won't understand. In the architecture, you should find evidence that where should I put this? Here? In architecture, you should find evidence that alternatives to the final organization were considered and find the reason for choosing the final organization over its alternatives. It is frustrating to work on a class when it seems as if the class role in the system has not been clearly concealed. That's crazy, right? It is frustrating to work on a class when it seems as if the class role in the system has not been clearly concealed. By describing the organizational alternatives, the architecture provides the rationale for the system organization and shows that each class has been carefully considered. One review of design practices found that the design rationale is at least as important for maintenance as the design itself. For details on different size building blocks in design, see levels of design in section 5.2. The architecture should define building blocks, the major building blocks in the program, depending on the size of the program. Each building block might be a single class, or it might be a subsystem consisting of many classes. Each building block is a class, or is a collection of classes or routines that work together on a high level functions such as interacting with the user, displaying web pages, interpreting commands, encapsulating business rules, or accessing data. Every feature listed on the requirements should be covered by at least one building block. If a function is claimed by two or more building blocks, their claims should cooperate, not conflict. Minimizing what each building block knows about other building blocks is key part of information hiding for details. See high secrets, information hiding. What each building block is responsible for. Should, let me try to do this. A lot of reading. Hopefully this doesn't block. Oh, no. Good, 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 good. He was in a good mood, man. Let's keep it as it was. Right? What each building block is responsible for should be defined. What each building block what each building block is responsible for should be well defined. Block can be a class well defined. A building block should have one area of responsibility. One area of responsibility. And it should know as little as possible about building blocks. Isolated. Blocks areas of responsibility. By minimizing what each building block knows about the other building blocks, you localize the information about the design into single building blocks. The communication rules for each building block should be well defined. The architecture should describe which other building block the building block can use directly, which it can use indirectly, and which it shouldn't use at all. We have major classes. The architecture should specify the major classes to be used. It should identify the responsibilities of each major class and how the class will interact with other classes. It should the class will interact major class and how the class will interact with other classes. It should include descriptions of the class in hierarchies, state transitions, and of objects persistence. If the system is large enough, it should describe how classes are organized into subsystems. The architecture should describe other class designs that were considered and give reasons for preferring the organization that was chosen. The architecture doesn't need to specify every class in the system. Doesn't aim for the 80-20 rule, 20% of classes that make up 80% of the system behavior. 20% of the classes are made up of the 80% of system behavior. Data design. The architecture should describe the major files and table designs to be used. It should describe alternatives that were considered and justify the choices that were made. If the application maintains a list of customers' IDs and the architects have chosen to represent the list of IDs using sequential access list, the document should explain why sequential access list is better than random access list, a stack or hash table. During reconstructions, such information gives you insights into the minds of the architects during maintenance. The same insight is an invaluable aid. Without it, you're watching a foreign movie with no subtitles. Data should normally be accessed directly by one, by directly by only one of the subsystem or class, except through the access data on the one. Troller abstracts away. This is putting on more detail, high secret information hiding. The architecture should specify a high level organization and contents of any databases used. The architecture should explain why a single database is preferable to a multiple database, or vice versa. Explain why a database is preferable to a flat file, identify possible interaction with other programs that access some data, explain what views have created of the data, and so on. Business rules. If the architecture depends on specific business rules, it should identify them and describe the impact the rules have on the system designs. For example, suppose that systems is required to follow a business rule that customer information should be no more than 30 seconds out of date. In that case, the impact that rule has on the architecture's approach to keeping customers' information up to date and synchronized should be described. User's interface design. The user interface is often specified at requirement time. If it isn't, it should be specified in the software architecture. The architecture should specify major elements of web pages formats, GUIs, command line interfaces, and so on. Careful architecture of the user interface make the difference between mail-like format and that's never used. The architecture should be modularized so that the new user interface can be substituted without affecting the business rules and output part of the program. For example, the architecture should make it fairly easy to log to log off a group of interactive interface classes and plugin group of command line classes. This ability is often useful, especially since command line interfaces are convenient for software testing at the unit of subsystem level. The design of user interfaces deserves its own book-length discussion, but it's outside the scope of this book. Resource management. The architecture should describe a plan for managing scarce resources such as database connection, threads, and handles. Memory management is another important area for the architectures to treat in memory-constrained application areas such as driver development or embedded system. The architecture should estimate the resources for used for nominal stream cases. In simple case, the estimate should show that resources needed are well within the capabilities of the intended implementation environments. In more complex cases, the application might be required to more actively manage its own resources. If it is, if it is, the resources manager should be should be architected as careful as any other part of the system. Security. For an excellent discussion of software security, see Writing Security Core, second edition, Howard and LeBlanc, as well as the January 2000 issue of EE Software. The architecture should describe the approach to design level and code level security. If a threat model has not previously been built, it should be built at architecture time. Coding guidelines should be developed with security implications in mind, including approaches to handling buffers, rules of handling untrusted data, data input from user cookies, configuration data, and other external interfaces, encryption level of detail contained in error messages, protecting secret that data that is in memory and other languages. Okay, non break.